Hello students, welcome to ePathshala. I am Dr. Shakila speaking on encapsulation of foods. Encapsulation is a process to entrap active agents within a carrier material, and it is a useful tool to improve delivery of bioactive molecules and living cells into foods. Encapsulation may be defined as a process to entrap one substance, which we can call as an active agent, within another substance, which is referred to as a wall material. The encapsulated substance, except active agent, can be called the core, fill, active, internal or payload phase. The substance that is encapsulating is often called the coating, membrane, shell, capsule, carrier material, external phase or matrix. Encapsulation of foods. Encapsulation was originally introduced in the area of biotechnology to make production processes more efficient, as the matrix around the cells allows for rapid and efficient separation of the producer cell and metabolites. Such technologies, developed approximately 60 years ago, are of significant interest to the pharmaceutical sector, especially for drug and vaccine delivery, but also have relevance for the food industry. In recent years, the food industry requires the addition of functional compounds in products. These compounds are usually highly susceptible to environmental, processing and or gastrointestinal conditions, and therefore encapsulation has imposed an approach for effective protection of those. Functional components are used to control flavor, color, texture or preservation properties. Bioactive compounds with various potential health benefits are included too. Encapsulation aims to preserve stability of the bioactive compounds during processing and storage, and to prevent undesirable interactions with food mass. Mainly, bioactive food compounds are characterized by rapid inactivation. These compounds would profit from an encapsulation procedure, since it allows down the degradation process with oxidation or hydrolysis, or prevents degradation until the product is delivered at the desired sites. Thus, the bioactive component would be kept as fully functional. Also, this technology may provide barriers between sensitive bioactive materials and the environment, and thus to allow taste and aroma differentiation, mask bad tasting or smelling, stabilize food ingredients or increase their bioavailability. In the food industry, encapsulation process can be applied for a variety of reasons. Encapsulation is a useful tool to improve delivery of bioactive molecules such as antioxidants, minerals, vitamins, phytosterols, lutein, fatty acids, lycopene and living cells such as probiotics into foods. In most cases, encapsulation refers to a technology in which the bioactive components are completely enveloped, covered and protected by a physical barrier without any protrusion of the bioactive components. In addition to the above, encapsulation can be applied for modification of physical characteristics of the original material in order to allow easier handling, to help separate the components of the mixture that would otherwise react with one another, and to provide an adequate concentration and uniform dispersion of an active agent. Encapsulation also constitutes a competitive tool to create new properties to usual materials. Many vitamins, plant extracts, unsaturated fatty acids are hydrophobic liquids. Mixing such components in a hydrophilic food powder can prove to be a real challenge. In addition to protection, microencapsulation allows the conversion of ingredients into a free-flowing, easily suspendable, example hydrophobic vitamins in fruit juices, and dispersible such as cocoa in milk powders. Encapsulation is a process to entrap one substance within another substance, thereby producing particles with diameters of a few nanometers to a material, the active agent, fill, internal phase or payload phase. The substance that is encapsulating may be called the coating, membrane, shell, carrier material, wall material, external phase or matrix. The carrier material of the encapsulates used in food products or processes should be food grade and be able to form a barrier for the active agent and its surroundings. There are two main types of encapsulates which are distinguished, that is the reservoir type and the matrix type as shown in the figure. The reservoir type has a shell around the active agent. This type is also called capsule, single core, monocore or core shell type. The latter is a combination of the first two. Only spherical shaped encapsulates are shown, but other forms are also possible. Here the active is indicated in white and the carrier material in grey color. The active in the matrix type of encapsulates might be in the form of tiny droplets or is dispersed at the molecular level throughout the particle. Application of pressure can lead to breakage of the reservoir type of encapsulate and thus to the release of its contents. Many encapsulation processes are based on making first droplets of the active in gas, liquid or powder form, and these droplets are subsequently surrounded by carrier material in a gas or liquid phase via different physico-chemical processes. Among all materials, the most widely used for encapsulation in food applications are polysaccharides, proteins and lipids, which are also appropriate for encapsulation. The most important criteria for selection of an encapsulation material are functionality, that encapsulates should provide to the final product, potential restrictions for the coating material, concentration of encapsulates, type of release, stability requirements and cost constraints. Materials used for the design of protective shell of encapsulates must be food grade, biodegradable and able to form a barrier between the internal phase and its surroundings. The majority of materials used for encapsulation in the food sector are biomolecules. These materials provide maximal protection of the active material against environmental conditions to hold actives within capsules, structured during processing or storage under various conditions, not to react with the encapsulated material, to have good rheological characteristics at high concentration if it is needed, and to have easy workability during the encapsulation. Among all the materials, the most widely used for encapsulation in food applications are polysaccharides. Starch and their derivatives such as amylose, amylopectin, dextrins, maltodextrins, polydextrose, syrups and cellulose and their derivatives are commonly used. Plant exudates and extracts are also used. Microbial and animal polysaccharides are also exploited. Apart from natural and modified polysaccharides, proteins and lipids are also appropriate for encapsulation. Among lipid materials suitable for food applications are fatty acids and fatty alcohols, waxes, glycerides and phospholipids. Let's explain encapsulation techniques which are commonly available for the encapsulation of foods. There are in fact a number of techniques available for encapsulation of food compounds. Since encapsulating compounds are very often in a liquid form, many technologies are based on drying. Drying are common techniques, and these techniques like spray drying, bed drying, fluid bed coating, spray chilling, spray cooling or melt injection are available to encapsulate active ingredients. Spray drying is one of the oldest and the most widely used encapsulation technique in the food industrial sector. It is a flexible, continuous and economical process. It produces particles of good quality which is less than 40 nanometers. This feature is desired from the standpoint of sensorial and textural characteristics of the final products. About 80 to 90% of encapsulates are spray dried ones. Rest of them are mostly prepared by spray chilling, freeze drying, melt extrusion and melt injection. Common examples of spray drying include fruit powders and various other kinds of pulp which are converted into powders. Extrusion methods consist of dropping droplets of an aqueous solution of polymer. Most often this is at the rate of 0.6 to 3% weight percentage of additives such as sodium alginate and active into a gelling bath. In case of alginate, gelling bath is 0.505 to 1.5 m calcium chloride solutions. The dripping tool can be a pipette, a syringe or a vibrating nozzle. Electrostatic extrusion, which is a very recent technology, is especially effective for production of very small particles down to 50 millimeters. An alternative extrusion technology, also called co-extrusion, which involves at least 2 or more ingredients simultaneously, might be utilized to prepare spherical microbeads with a hydrophobic core. Another frequently used technique is emulsification. It is used in the case of water-soluble food active agents, and there are two combinations of emulsions that are commonly available: water-oil emulsions or oil-water emulsions and water-oil-water double emulsions. An oil in water emulsion can be dried by different drying methods as mentioned above, such as spray drying or freeze drying, and thus to produce a powder. Such dried emulsions might be encapsulates or an instant formulation of numerous food products. Common examples here include soup powders, fruit juice powders and vegetable powders. Spray chilling or spray cooling are technologies to produce lipid coated active agents. The difference between these two techniques is the melting point of the lipids. In case of spray chilling, it is in the range of 34 to 42 degrees centigrade, and for spray cooling the temperature would be higher. The agent could be dissolved in lipids present as dry particles, or they may be present in aqueous emulsions. Spray cooling is a technique with possibility to achieve high yields and can be run in both continuous and batch processing methods. Equipments for spray chilling and spray drying are available in today's market, and these provide extensive support for the production of such functional foods. In case of spray chilling, the particles are kept at lower temperature in a setup similar to the fluidized bed spray granulation. Fluid bed coating is an encapsulation technique where a coating is applied onto powder particles in a batch processor or a continuous setup. The advantage of a fluid bed coating is that the color of the materials is retained, and this can be easily be applicable to green leafy vegetable and such kinds of powders. Fluidized bed coating is achieved by an upward airflow through a bed of particles and spraying a liquid with shell material. The powder particles are suspended by an air stream at specific temperatures, which may be ambient, and sprayed with an atomized coating material. The coating material might be an aqueous solution of cellulose or starch derivatives such as amylose, amylopectin, and it could also include proteins and gums. The particles to be coated by fluid bed should ideally be spherical and dense and should have a narrow particle size distribution and good flowability. Hence, the most common applications here again would be fruit juice powders, which have a good flowability characteristic. Spherical particles have the lowest possible surface area and require less coating material for the same shell thickness than non-spherical ones. Vacuum and freeze drying operations, which occur at temperatures above the freezing point of the solvent. The major disadvantage of freeze drying are the high energy input and long processing time. Moreover, vacuum and freeze dryers are expensive and cannot be used at the laboratory scales and for research purposes. In addition, during processing, a barrier with an open porous structure between the active agent and its surroundings is formed. Examples of microencapsulates in food products. One of the most common reasons for encapsulation of active ingredients is to provide improved stability in the final food product and during processing. For example, probiotics, which are live organisms, remain highly sensitive to a variation of pH, mechanical stress, transport condition, and digestive enzymes in the stomach. Probiotic bacteria are defined as live microorganisms and bioactive food components with serious health benefits in the host if they are present in adequate amounts. More commonly, probiotics are used as cultured milk beverages as well as incorporated into food powders along with vegetable and fruit systems. A choice of an encapsulation system is always crucial since it has to be efficient and easily incorporated into the food without interfering with the texture and taste of the food. Also, some microbes such as the lactobacilli and bifidobacteria, which are the common types of probiotics in the Indian food industry, seem to benefit from encapsulation matrix during dehydration and lyophilization, which also is freeze drying and spray chilling process. One among the gentle approaches for encapsulation is the extrusion technique, and in combination with matrix molecules that preserve or even promotes the functionality. This technology is advisable for probiotics, especially when they are included with fruit juice powders. Except extrusion, commonly used encapsulation techniques are spray, freeze, or vacuum drying, each of which is an expensive technique and can be done only under controlled conditions. Typical carrier materials are mixture of carbohydrates and or proteins, including microbial gums, gels, and alginates. Usually, protein isolates, gum arabic, pectin, skim milk powder, non-fat dry milk solids, soy, modified starch, maltodextrin, and sugars are employed. Looking at other benefits of encapsulation, the main advantage rests with less evaporation and degradation of volatile actives such as aroma, which usually contains mixture of volatile and odorous organic molecules. Besides, flavors are usually expensive and therefore manufacturers are usually concerned about the preservation of aromatic additives. In addition, packaging of these kinds of foods appears to be a major challenge, especially when probiotics are combined with alginates and other kinds of microbial gums. Thanks to encapsulation, a food compound such as aroma is covered with a protective wall material and against evaporation. Chemical reactions such as flavor-flavor interactions, light-induced reactions, oxidations, rancidity, or migration in food materials. Flavor encapsulation can be accomplished by a variety of methods like spray drying, spray chilling, freeze drying, spray cooling, spray bed drying, and others as mentioned above. Spray chilling is a very recent and convenient technology to produce lipid particles which would be covering up with the aroma and other kinds of sensory characteristics. Since the flavor is one of the most important characteristic of food, the ultimate goal of encapsulation is to control the aroma release components and to improve the stability during processing and consumption of the final product. This becomes very important especially in sensitive fruit and vegetable powders. In general, aroma releases from food before and after eating, which depends on the aroma features and physical state of the matrix. Also, another goal of employing encapsulation is to prevent reaction with components which may be present as additional additives in food products, such as environmental oxygen or availability of the water activity in case of essential oils. In fact, essential oils are slightly soluble in water and they transfer to the water their odor and taste. This way, the water activity of the food products gets reduced, and in the process, other kinds of untoward reactions set in. Hence, it becomes very important to consider that essential oils that contain terpenes, phenols, alcohols, aldehydes, esters, ketones and other components be safely enclosed within the carrier material in order that their sensitiveness is regained and released at controlled rates. Essential oils have a wide spectrum of biological activities, including growth inhibition observed against bacteria, yeast and fungi. These can be easily identified by proper microbiological analysis when the food products are subjected to quality control and proper packaging techniques. The encapsulation of essential oil into different nanospheres has been used as a controlled release vehicle with site-specific delivery properties to maximize antimicrobial activity of the oils. To conclude, encapsulation is a technology providing an effective method to cover an active compound with a protective wall material called the carrier, and thus it offers numerous advantages. These bioactive components include, as mentioned, lipids, vitamins, peptides, which comprises the protein components, fatty acids, antioxidants and antimicrobials, minerals and living cells such as probiotics. Some of the main benefits are protection of various actives against evaporation, chemical reactions such as rancidity or migration in food, controlled delivery release processes, preservation of stability of the bioactive components like carotenes or luteins during processing and storage, prevention of undesirable interactions within the components present in the same food product, and masking unpleasant feelings during eating. Encapsulation is therefore an important approach to meet all demands by delivering bioactive food components at the right time and right place. One attractive possibility for this remains to use a methodology where two or more bioactive components could be combined to have a synergistic effect. It may be foreseen that encapsulated bioactivities could play a significant role in increasing the efficacy of functional foods over the next few generations. With advanced strategies for stabilization of food ingredients and development of new approaches in today's food research, we would be able to improve nutritional properties and health benefits of food compounds, including the probiotic incorporated foods. The success of an encapsulation process is often linked to the exact know-how of the formulation or of the chemistry to achieve stabilization. This is especially the case in the food industry, where the number of acceptable materials is very limited. Hence, developing an encapsulated product remains a challenge even today, requiring a multidisciplinary and integrated approach. This is where food engineering and food processing play a major role, where fabrication of the nanocapsules becomes a great challenge. Many encapsulation technologies currently exist, but many of them are still at the development stage.